So yeah, thanks for actually showing up. So Phil tells me there was a large drop. I mean, there were probably a few more people last time I was here. So is it something I said? Yeah, Phil told me there's a significant drop in attendance when you start putting the lectures online with videos. So if you're at home when watching this, shame on you. But to benefit those who showed up today, like this is going to be a more sort of theoretically oriented lecture, trying to talk about concepts of memory in deep learning rather than about spoon feeding you models and the actual details of particular models. Although I will go through a bit of maths, but I will, like in the next few days, or perhaps in a week and a half because I'm going on holiday, put a pretty comprehensive bibliography up if you want to read the papers. And to benefit you who have bothered to show up today, let's try and make this interactive. So if you have questions or points that you find outrageous, then feel free to interrupt me politely and we can talk about it. I think we'll try and finish this in like an hour and a half, but we'll see how many questions there are. So memory is a pretty central component about how we interact, not just with text, but with when we're reasoning, when we're incorporating information. We tend to selectively remember salient information and forget what's useless, but we often appeal to things that we've experienced to be able to draw conclusions. So it stands to reason that memory would be a pretty important aspect of natural language understanding and natural language processing. Throughout this course, you've seen memory already in a variety of forms. Attention in Carl's lecture the other day, LSTMs in terms of capturing long-range dependencies more aptly with recurrent neural networks. And today's lecture is an invitation to step back from the details of these models and try and see what unifies them, to provide some inspiration for developing your own models, or at least a better sort of high-level understanding about what all these models are doing in the literature, since it's a fast-moving field. So today I'm going to briefly have a little recap about what we call the transduction bottleneck in sequence-to-sequence modeling, and try and sort of explain how recurrent neural networks in their most basic form are limited in a way that induces this bottleneck. I'm going to invite you to rethink RNNs not as a particular class of models, but kind of as an API for designing models. And then in the second half of this lecture, I'll describe how attention and register machines like memory networks and neural Turing machines and differentiable neural computers and other sort of more esoteric memory-based mechanisms kind of fit this API. So that you can, when you read papers, which you should be doing as part of this course to understand the actual mathematical details of these models, you can sort of think at a high level, it's like, this fits this kind of general schema. It's like, I can see how these things are related. And hopefully see through some degree of BS that you see in the introduction to these papers claiming they're solving everything. So let's start with the bottleneck. So this is, Chris Dyer pointed out that my RNN diagrams look like little men, so I had a little hat and mustache. I promise is these. Well, actually, I won't promise this is the only crap joke in this lecture, but it's one of them. So recurrent neural networks, which you've seen throughout this course, to remind you, if you've really been sleeping for the last few days, are ways of designing neural architectures, or they're component of neural architectures that allow us to process sequences of variable length. And you can think of them as sort of processing units that take inputs and then produce outputs. So for example, a distribution over what the next word is given the history. And they track history by having a loop, a recurrence, so by updating their own state and sharing parameters across the transformations that update their own states. So conceptually, you can think of the activations of a hidden layer in a recurrent neural network by connecting back to themselves are modeling the history of a sequence, or of a set of sequences. They fit variable with problems well, which is why they're so popular in natural language processing and natural language understanding. And you sort of unfold them through time to basically think of them as feed-forward network with a lot of shared structure and shared weights. And different varieties of these that you'll have seen in the course can capture long-range dependencies. There are some obvious RNN applications which you'll have seen in this course. So language modeling, predicting the log likelihood of a sequence of English or Chinese by decomposing it, by factorizing it into sort of conditional probabilities of what's the probability of the next symbol given the symbols I've observed or generated so far. Sequence labeling, which you can think of the online variant of this. sentence classification, so just read in an entire sequence of symbols and predict a label. These are all nice tasks which RNNs are kind of work out of the box for. But for each of these individual tasks, there are sometimes simpler or better or more sort of tailor-made models. What's nice about RNNs, about operating on these sort of, being able to model these probabilities in a nice continuous space, is we can condition this decoding mechanism on any arbitrary data. We can model this conditional probability of a sequence of text given arbitrary representations for which we have, arbitrary elements for which we have vector representations, which I named beta here to not talk about any specific domain. And you can influence the decoding by linking beta as the start state of a decoding process, by feeding it as extra input, by concatenating with the output. There's a bunch of different ways. This idea of conditional language modeling it has influenced a lot of work on transduction, and transduction problems are at the heart of a lot of natural language understanding problems. Like translation is you're observing, for example, a French sentence, you're producing a representation beta for that sentence, and from that you want to decode into English. So that's what a translation system does at a very abstract level. Parsing you could also see as this form of transduction where you observe a sequence of English and you want to transduce that into a set of brackets or pause tags with some hierarchy to extract what the latent tree is. And there are even some sort of, if you really want to see everything as a transduction problem, even things like computation can be seen as transduction problems where you read some input data, you produce a representation of it, and then you decode into the output of the computation. This kind of approach to transduction, which is frequently referred to in the literature as sequence-to-sequence mapping, can be described generally as saying you have a set of source symbols, which could be, for example, your French sentence, and you want to map those into some sort of target sequence. So, for example, the words of your English translation of the French sentence. How this has been done in the most basic form is that we are going to produce a representation for a source sequence S, and then we're going to model the conditional probability of the next symbol of the target sequence, so for example, your English sentence, conditioned on S and what we've translated or decoded so far. I'll skip this. So, I mean, in the case of translation, this is pretty much exactly what I've just described. People like the work by Sutskever and Nips in 2014, or Kauschberger and Blunsom, have sort of produced this encoder-decoder framework where you're going to read in, if you want to translate French into English, you're going to read into an RNN the words of your French sentence, word by word, and update your hidden cells. So here I've unrolled the RNN, but you can imagine that all these arrows from left to right are shared projections or shared weights. And at the end of your, oh my gosh, what's this? At the end, when you hit a delimiter symbol or an end of sentence symbol on your French sentence, indicating that you're switching modes, your RNN starts outputting English words and feeding back what you've sort of generated as the next input. So you can imagine this as running an RNN over a single sequence that's concatenated French and English, but you only really care about the outputs when you're in decoding mode. And this has produced some fairly convincing, or at least fairly impressive at the time, results in machine translation, because we didn't really think that neural networks should do this sort of thing. I said anything under the sun can be cast as transduction, and this paper by Zaremba and Sutskever in 2014 kind of followed this maxim. So they thought, okay, why don't we use this exact same architecture we use for machine translation and do computation with this. So the inputs, instead of being sentences of French or English, were smallish Python scripts, and the outputs, instead of being a translation of those Python scripts, were the result of the computation. So there were incredibly strict constraints on what sort of Python code you'd put here, so it's not full-blown Python. You can't have nested sort of loops. But the fact that this worked at all sort of, I think, blew a lot of people's minds, that you have a single network that reads the Python script character by character and outputs the the result of the computation character by character, was very impressive to many people. Now, if you read the paper carefully, you should take these results with a grain of salt, because when you're training sequence-to-sequence models or even language models, we operate under a teacher forcing style training where we feed the correct output of the last time step as an input to the next time step of the RNN. But during testing, you feed in what the model predicted or what the sample from the model was at the last time step as the input. Here they did teacher forcing during testing, so it was, even if it was completely off at the previous time step, it's put kind of back on track by being fed the right number. So there's a bit of fuzzy, like I don't want to say BS, but the evaluation wasn't exactly up to scratch. But the fact that this kind of worked was already pretty impressive. So it sounds like this kind of model, this very generic kind of sequence-to-sequence model, can do a lot of stuff. People also investigated how, instead of translating English into French, we could just translate English into the parse tree. This is Vignel's al. Grammar as a foreign language. So what's wrong with this kind of model? Well, there's a bottleneck between the source and the target when you're doing this transduction. By bottleneck, we mean that all the if you look at this, even though we're unrolling it across time, all the information required to decode the English sentence given the French sentence, so all that information about the source, has to be present in the activations of the network at this particular time step. The activations of the previous state only matter during training, but when you're doing inference, when you're decoding, all the information needs to be here. So this is an example of non-adaptive capacity. As you can imagine that as the source sentence grows, so if you try and translate longer and longer bits of French, you would have to compress more and more information into this fixed size representation here, and therefore you'd imagine that since there is no ideal infinite compressor, that when you're decoding you're going to get bigger and bigger losses unless you make your network bigger. So there's this undesirable property that the size of your representations, the size of your hidden layers, needs to kind of map onto the data, and it'd be nice to be able to break that kind of bond. On top of that, we observed that when we train these models, so we're just a standard sequence-to-sequence models, and apologies if this was covered in previous lectures in detail, that during a large part of the training, the target language model is what's being learned first. So by this, we know if we're doing if we're doing French to English translation, it's first going to learn kind of what an average sort of English sentence looks like. It's going to, before it actually starts propagating dependencies back into the source and actually conditioning on the source properly. So you spend a lot of your time just learning an English language, a marginal language model, and only a small sort of part of your time actually learning the dependencies towards the end of training. One way of seeing this in terms of learning is that you're getting a rich gradient directly close to the classification decisions you make here when you're deciding which character, what the distribution over words is. And for gradient to flow back to the activations, to the weights over here and capture the dependencies, it needs to go through all these nonlinearities through your network. And that's why you sort of have gradient starvation on the encoder side, and it takes a while to learn that aspect. So let's think about this from a computational perspective. Am I missing something? Oh yes. So before I jump into this this computational perspective, who here has done the models of computation course here? Okay. Who knows? Who has no idea what a finite state machine is? Okay. Great. Okay. Everyone has some vague idea. Okay. Cool. So you may remember from your undergraduate or your earlier year studies, if you're still an undergraduate, that there's a hierarchy of models of computation. And that to each model of computation, there's a corresponding sort of class of formal languages that model of computation can express. So finite state machines are just transitions between a finite number of states, and that models the class of regular languages. So a finite state machine models a regex, or regular language. If you add a stack to a finite state machine, you get a pushdown automata, which corresponds to the class of context-free languages that you might generate from a context-free grammar. And then if we skip a few steps up, we get to Turing machines, which are the more powerful model of computation, which most of our computers are based on theoretically, and that the corresponding language classes recursively enumerable languages or computable functions. So by show of hands, who thinks that RNNs are, an RNN you can think of something that's computing. So it's modeling the history of a sequence or some source, and it's outputting a target sequence. Where would you say an RNN is on this computational hierarchy? So show of hands, who thinks that it's like kind of a finite state machine? Okay, here we go. Who thinks that an RNN is kind of like a push-down automaton? Okay, and who thinks that an RNN is like at the top, like it's like as expressive as a Turing machine? And everyone's like kind of like, I can barely see your hands here. It's like, okay, Turing machines, hands up. Okay, great. Okay, so there's quite a few people who think it's at the top. So if you read the neural Turing machines paper, you'll see that there's this reference to this Siegelman and Sontag paper from 1995. All core research was done in the 90s. That stated that RNNs are Turing complete in a way. And I'm actually not going to go through this sketch of this proof in detail because on reflection I'm not sure it's completely correct. But there's a proof in that paper that any Turing machine can be encoded as an RNN if you set the weights just right, and that therefore any RNN could learn in its activations a particular class of Turing machines. Not necessarily every class of Turing machine, every Turing machine, but that if you're allowed to vary the size of your hidden representation, you can encode bigger Turing machines and therefore solve cool problems. So you'll have learned earlier on in this course, hopefully someone's mentioned this, or when you did a machine learning course before this, that feed-forward networks are universal function approximators, which means that for any function, if you have a big enough feed-forward network, you can get an arbitrary sort of bound with the actual function. You can express an arbitrary error bound. But being able to express any function, and in this case, an RNN being able to express a Turing machine is not the same thing as it being able to learn it. So the key point here is that if you wire the RNN just right, it's expressing a Turing machine. But that doesn't guarantee that you're going to be able to learn from data that very precise kind of wiring, that very precise set of weights. Does anyone find that controversial? No, great. Okay, so this slide's more of an opinion, so we do that sometimes in lectures. This is not something I want you to take as unchallengeable truth. But I'd like to argue that simple recurrent neural networks, and by that I mean like a sort of vanilla RNN with 10H, gated recurrent units, and even LSTMs, cannot, through normal sequence-based maximum likelihood training, learn Turing machines. There are several reasons I make this argument. The first is that RNNs don't really have a notion of an external tape they can control. You're sort of seeing inputs as they're fed to you by your training mechanism. You can't go back and revisit previous inputs. You can't sort of arbitrarily do no-ops and update your internal state. They operate in lockstep with the sequence they're being run over. Maybe a bit of a weaker argument is it seems a little, the sort of training objectives we use for this, so maximizing the likelihood of the target given the sequence and sequence-to-sequence modeling, or maximizing the likelihood of a sequence when you're using language modeling, is going to produce a model that's very close to the training data distribution. So there's no sort of particular impetus for this training procedure given the high expressivity of our models to learn something that generalizes beyond that, as we'd want if we were learning something general like a Turing machine. And obviously we can regularize these models by putting sort of penalties on having the norm of your weights be too high or too low. You can try and induce sparsity in the weights with L1 norm, with L1 penalties on the weights. But it's insane, or at least unreasonable, to expect simple regularization mechanisms like this to yield very, very structured wirings or sets of weights that would express a Turing machine that would express good out-of-sample generalization. So instead, again, this is more of this is more an opinion than a proof. But I'd invite you to think of RNNs as being much closer to approximations of finite state machines. In a sense, RNNs, so if you're just learning a language model, for example, are effectively learning order n Markov chains, but n doesn't need to be specified in advance. In contrast with log bilinear models. Did you do log bilinear models at any point in this course? No? Okay. In contrast with, do you know n-gram language models? Yeah, okay, great, cool. So n-gram language models, you have to specify what your order n Markov assumption is. I'm saying for RNNs, you don't, but it still exists. It's sort of, in a sense, specified by the data. If this is true, then you can think of LSTMs, RNNs, GRUs as being, in theory, memoryless, but they can simulate memory through dependencies. So if you have like a regex like dot star a dot 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 a, this can in turn, the recognition model can in turn be turned into a generative model that says, I have a distribution over the probability that the next symbol is A, given that A was seen 4 symbols ago. So that seems to be saying, I can remember that 4 symbols back. But that's not the same thing as sort of a general concept of memory. You're just capturing a fixed width dependency in your model. So in a sense, if you really want to see this as memory, RNNs, as we use them, as we design them on their own, can express a very limited, bounded form of memory, but there's no incentive to learn something beyond the range and the range, length, structure, and complexity of dependencies observed during training. And so there are some problems with this kind of paradigm. If RNNs are just finite state machines, the RNN state has to act both as a memory, since it needs to capture the dependencies in its activations, but also as a controller, as it needs to keep track of what those dependencies are, when to free up the information, when to allocate new information in memory. So it's serving 2 functions at once. On top of that, the more longer range dependencies you need to capture, the more memory you're going to need intuitively, because you're going to need to keep track of how far you are from when you observed, for example, a symbol, and when you need to output something conditioned on that position. Tracking more dependencies intuitively will require more memory, so if you have a model that needs to capture an increasing number of arcing dependencies, that needs to store that information somehow, and again, a fixed size. RNN hidden layer is going to be bounded in terms of what information it can store, and then without destruction of information through compression. And finally, more structured or complex dependencies need more memory. So if you're trying to capture very complex interdependencies in your source, and then use that to produce more accurate translations, it's reasonable that your RNN size would need to be bigger and bigger. And ultimately, even if none of these things are a concern for you because you have a very big computer, finite state machines are pretty basic in terms of what they can do. Now, to link this back with natural language processing, you may have heard linguists debate whether or not where on this hierarchy of formal languages that's connected to the computational models hierarchy I talked about earlier, where natural language stands. So a lot of people think that natural languages like English are at least context-free or perhaps weakly context-sensitive. So they need to be modeled by something like push-down automata or above. Some languages like, I think, Dutch are considered to be higher up on that hierarchy. I'm not a particularly well-trained linguist, so I don't actually know how much of this is true from the bibliographical sense. But and some people argue that English, and in fact all these languages, are just, they're just regular languages. That there's no real sort of need for this these higher order grammars to understand natural language. Even if it's true that natural language is regular, that it's not context free, it's useful to be able to model more complex computational models with our RNNs or with our neural networks for reasons of rule parsimony. So, for example, let's take the simplest language, which is context-free, or at least one of the simplest languages, which is context-free. So that's not recognized by a regular expression or by a finite state machine, and that's A and Bn. So that means that there's an unbounded number of A's and there's a matching number of B's. If in practice the number of A's you see, and therefore the number of B's is actually bounded, which you might imagine is, practically speaking, if people were using this as a communication protocol and after some time if they took too long, they'd die or get hungry or lose track of what they were doing. So if it's bounded by some maximum number n, then this becomes regular again. The regular language that would be used to capture that sort of bounded version would have n+1 rules. So you need to match the empty string, AB, AABB, AABBB, and so on, up until capital N A's followed by capital N B's. Whereas the context-free grammar has 2 rules, or 3 if you want to include counting, which is just match this sort of recursion and then match occasionally the empty string to terminate the recursion. And you might need an extra rule to count. So if you think about what your network is doing, when you're training the network, if it's internalizing something like rules or approximating rules, what do you think would be more complex to learn? Something that requires internalizing n+1 rules, or something that requires internalizing just 2 rules? And the intuition here is that if our models are more expressive, not in terms of like how big the hidden layer is, because we already know that. I mean, RNNs in general, deep networks are universal function approximators. But in terms of what sort of class of computation they can model, so what sort of rules it can internalize. If it's biased towards something that looks like a CFG, then you think, okay, maybe it can actually learn more general rules. We can introduce an inductive bias by moving up in the hierarchy. So in a sense, with LSTMs, deep LSTMs, GRUs, or your favorite variant, we're kind of stuck here at the bottom of this hierarchy, and we'd like to be somewhere up there. How long have I been talking? 4:35. Okay, we're doing pretty good for time. Are there any questions at this stage? Okay, I haven't said something like so outrageous that is anyone completely lost? Have I said something really stupid? All right. No, perfect. Yes?
I know, like, when I learned about neural networks a long time ago, I can't remember the always saying, like, it's kind of like the iterative model is actually like a higher order machine, kind of like a Boltzmann kind of machine.
I mean, so there's restricted Boltzmann machines, which are a little like neural nets. Jeff Hinton worked on this, Russ Salakudinov. In terms of where Boltzmann machines are on the computational hierarchy, I'm not actually aware of any literature that's tried to relate those, but then again, I don't have complete coverage of literature. I tried to look it up, like it didn't really, yeah, that's a good question. No one's brought up Boltzmann machines when I have this slide before. I'll think about it. But that's a good question. This was the question slide. Perfect time. Okay, preempted that one. Any other questions? Yes?
I'd love to hear any intuition you have on why sometimes things are learnable versus representable. Like even if it's representable, why it might not be learnable.
It's a really deep question. Gosh. I think I'm too sober to answer that one. Am I supposed to be saying that? No. Why something is representable versus learnable? I mean, that's a very general question. I'm not quite sure I know how to answer it. I mean, okay, I guess connecting it to the argument I'm making here is like some problems. The complexity of the problem, the problem might be describable by a finite state machine, right? But I want to decouple the computational, where in the computational class is the minimum sort of level of complexity that you need to express the solution to the problem, which would be a finite state machine in the case of this, and what's the simpler one. And so here by stepping up, even though it's like more power than you need, I think this means you can express the solution in fewer rules. And if we think about RNNs enhanced with some form of memory such that they could capture context-free grammars or model push-down automata as being able to internalize these rules, it should make the problem more learnable. It just needs to internalize 2 rules versus n+1. So that's that's not approved. In a very hand-wavy sense, that's the sort of distinction I'm trying to make here. As to what actually makes what makes a problem fit here rather than here, that's dependent on the complexity of what the generative process is, right? For language, we don't really know if it's regular or context-free, so why not step up in the hierarchy a bit and see if it makes it easier to learn the structure of language.
So at risk of muddying the waters a bit, so context-free grammars are a great example of something representative. Not actually learnable. So context-free grammars are not learnable in the living. But that's what Ed's talking about here is practical learnability.
Yeah. So
if you're interested in these sorts of things, there's a great course that Varun is running right now on statistical learning theory, which goes into all these questions. I think it's called advanced machine learning, but basically it's learning theory.
Isn't that what was called basic machine learning last year?
Yes.
Oh my gosh. We need a better system here. So we definitely are talking about practical learnability. So I mean, in terms of can you tractably learn regular language induction is a solved problem. Context-free language induction is a formal problem. As Phil pointed out, intractable, or at least is that proved intractable?
Yes.
Okay.
Figure out not
Great. Okay, there. Then honorable. So, but that's not the sort of like this. We're talking about whether in practice you can find an approximate solution that's sufficient. Okay, so let's revisit RNNs more as instead of individual kind of ways of specifying the cell, which is what you see here. So this is like like a vanilla RNN. If you put a 10H update, and these are just linear projections, and this is just a linear projection of the vocabulary in a softmax. That's an actual individual sort of architectural choice. If we step back and see this, what an RNN is as something that just satisfies this API, we can start to think more generally. So abstractly, an RNN is something that takes inputs and produces outputs, and that maintains state, right? And if you're implementing stuff in TensorFlow and in PyTorch and a bunch of these sort of like higher level neural network libraries, this is kind of the design that people are following, saying it's like, okay, put whatever you want in here and then pass it to an unroll operation, and you'll be able to do forward and backward passes on it. And within this kind of box, you can put arbitrary complexity. So if this was a simple RNN, you can notice that an LSTM, which I've made purposefully complex from a diagrammatic standpoint to show that there's a lot more happening, still fits the API in that there's inputs and outputs. State, which is the cell state, and the hidden state after the nonlinearity is passed through here. And then all the operations inside are just ways of wiring these different arrows to one another. So we're modeling each recurrent cell, stepping back from the individual ones we looked at, is abstractly modeling a sequence from inputs and previous states and producing a sequence of outputs and next states. And usually the previous state domain is the same as the next state domain, and the input domain is somewhat related to the output domain, but these things can be untied. And all we need to do for this API to be part of an end-to-end differentiable system is satisfy the constraint that all the gradients of the input of the output error with regard to the input, with regard to previous state, and the next state error with regard to the previous state and the inputs, that all these particular paths are differentiable through the internal structure we have, so that all those partial derivatives are defined. So to summarize this kind of notion of stepping back and making it into an API, we want to explore throughout the rest of this lecture different sort of wirings we can put within this box, such that things are kept differentiable, such that the state sort of tracks the overall state of our machine, and what we're doing in the cell is actually exhibiting the computation, so we can start adding sort of elements of memory in there. This is a bit more high level than I wanted. We're also going to now we sort of step back from like what's actually happening inside, and we can be a bit more free as long as we satisfy this general API. We can start thinking about there being a split within this. If we wanted to enhance RNNs with memory, we're going to explore different forms or different models that sort of satisfy this general blueprint, where we're going to have a controller within our RNN cell that's dealing with input and output, and we're going to have a memory, and there's going to be some form of interaction between the controller and the memory. The controller itself might be like an LSTM, so it has its own state that it needs to preserve through time, and the memory likewise is going to have its own state, which might be mutable or immutable, and that's going to be preserved through time. So you can think of the previous state of your overall RNN as decomposing into the previous state of your controller and the state of your memory. Let's start with attention. So in the last lecture, if I'm correct, Carl Moritz introduced you to the notion of attention. Thinking about what attention is abstractly is you have an array of vectors that represents some data that was produced by some mechanism. Your controller, which is your LSTM and your decoder and your attention sequence-to-sequence model, deals with both the input and output logic, but also provides some way of extracting information from your attention matrix. And you want to be able to therefore read your data you want to be able to read data from your memory array selectively at each time step and accumulate gradients in your memory on the backward pass. So there are different forms of attention that may have been described to you. The first is what we often call early fusion. So they're based on the previous state of your controller. a vector is going to be produced from your memory and concatenated with the inputs to the controller in order to produce the output. And then the next state of the controller and the memory never is read-only, so it doesn't change, are going to be repacked and produce the next state, which in turn will allow you to retrieve what the next read will be. Early fusion can be thought as the controller gets to look at the state of the memory based on a query produced by its previous state before updating its own internal state. So you're making a non-Markov assumption about tracking. You're tracking the history of your attention. Mathematically, what this translates to is, I won't go through this in a painful amount of detail, but you're going to unpack your previous state is going to be your previous controller hidden state in your memory. Oh yes, sorry. Did late fusion here. Did I get these the wrong way around? Okay, I'm going to fix the math and another thing. I'll just talk you through this directly on the slide. So you read at the beginning. You're gonna have a start state. You're gonna which way should I put this around? So based on the previous state of your controller, here we are. We're going to take some sort of inner product, parameterized inner product, or other similarity kernel with each vector in your memory and produce a logit. By softmaxing, we basically have a distribution over the positions in your memory. You could see this as like parameterizing a distribution over the memory, but because we want to keep things end-to-end differentiable and ways to differentiate through stochastic decisions is a slightly more advanced topic, which we're not covering in this course. Attention will take a sort of mean field estimate of the state of the memory according to that distribution. So you're simply going to, according to the probability of each slot, you're going to take the weighted average of all the values in the memory, and that's going to be a vector that's going to be concatenated with the inputs to the RNN and update your internal state, which in turn, at the next time step, will serve to retrieve another vector from the memory. And that's responsible for doing the outputs. Late fusion, in contrast, is a similar kind of process, except the current state of the RNN is going to be used to retrieve information from the memory. And then we're simply going to concatenate that with the output of the RNN to predict the next word. So whereas here, we're keeping track of the history of attention within the RNN, here we're making a Markov assumption in that we're just concatenating the output of our attentive process with the output of the RNN and jointly making a prediction over what the outputs, for example, the next word should be. Abstractly, you can think of attention as being sort of a read-only memory. The encoder, in a sequence-to-sequence model, the encoder will be tasked with the job of producing an array of representations. So, for example, one sort of vector per token. The interpretation of this vector is that it's both the content that's going to be retrieved by the attention mechanism and also a sort of semantic index for that position, which is going to be, because we're by taking the inner product with the controller state, we're retrieving the likelihood that there's a match at that position. The representations are packed into this attention matrix, and the decoder is the controller that's basically affecting those operations. So this has some nice properties in that this has some nice properties in that, as I'll show you in the next few slides. This bypasses the transduction bottleneck we saw at the beginning of the lecture. The encoder isn't gradient starved because there's a different pathway for gradient to pass to the encoder states. You can think of attention also as like computing soft alignments between sequences. So if you've taken a course on sort of more traditional machine translation, the job of the attention mechanism is to say, when I'm producing an output token in, for example, English, what word or what sort of set of words, if you're doing soft attention, am I basing that decision on? What words am I translating in sense? So in the standard sequence-to-sequence model, we saw that all the information required to decode into English needs to be present in this hidden layer. If we enhance it with attention, the encoder, when it was running forward, as I said, in the standard sequence model, we didn't really care about what these activations were unless we were doing except during training. During the forward pass, we actually want to preserve these and use them as the activation, as the attention matrix. So when we're decoding based on our hidden layer activations at any particular time step, we're actually looking back upon the past to see what the best match is amongst the French words when deciding what to translate. Because this is not a differentiable operation, gradient is flowing from the particular decisions of what to generate, not only through the activations of the RNN, but also through these attentive decisions. And so gradient is coming directly to the top bits of, well, basically to the output states of the RNN during the encoding phase, rather than having to go all the way through the nonlinearities. A few applications of this. So you may have seen applications in Carl's lecture, but some applications of this that he might not have covered. Did you cover textual entailment? Okay, great. So machine translation is obviously one good application for this. Recognizing textual entailment is another sort of task where this has been successfully applied. So recognizing textual entailment is the task of, you have a pair of sentences. One's called the hypothesis, and one is called the, what's the word I'm looking for? Conclusion? Yeah, so one's the hypothesis and one is the conclusion, and you want to see if there's what the relation between these two sentences is, whether the hypothesis contradicts the conclusion, whether there's no relation, or whether the hypothesis entails the conclusion. Premise and hypothesis. Oh my gosh, sorry, it's a long day. So so you observe a premise and then you observe a hypothesis, and you want to see if the premise entails, contradicts, or has no relation to the hypothesis. So it's quite a hard task if you think about it, because there's a lot of ambiguity, and you sometimes need to rely on world knowledge or sort of common sense. So if you see, like as a hypothesis, a man is crowd surfing at a concert, as a premise, and then you see the hypothesis, the man is at a football game, well, that's a contradiction, right? Because we know that concerts and football games are different events. If you see a man is crowd surfing as a concert as a premise, and then the hypothesis is the man is drunk, well, that's plausible to you and me, but that's not actually in a logical sense entailed, so that's neutral. And then if you see a very simple form of entailment, so if the premise is the man is crowd surfing at a concert and the hypothesis is the man is at a concert, which is subsumed by that, then obviously it's entailed. Likewise, a wedding party is taking pictures. You'd see a contradiction if the hypothesis was there's a funeral, but that requires knowing the relation between wedding parties and funerals, being different kind of events. Being outside, well, that's plausible given the premise, but it's not entailed. So that's, I think, where a lot of difficulty comes from. And then someone is getting married again. You need to know the relation between weddings and the concept of marriage, or at least the word married, to detect that there's an entailment. You could do this as a simple sequence-to-sequence task, and some of the first end-to-end approaches, as a sequence classification task. So some of the first end-to-end applications would simply run an LSTM over the premise and then over the hypothesis, and then based on the final state as a sentence representation, classify into one of three classes, into contradiction, entailment, or neutral. If you enhance it with alignments, you can start to sort of learn word-to-word or many-to-one or one-to-many correspondences. So we read the premise, and while we're reading the hypothesis, we allow the system to look back to the premise and see if there's anything that triggers a contradiction or triggers an entailment relation, allowing it to better classify at the end. Attention allows us to visualize what to some degree what the system is thinking or what it's basing its decision on by looking at a heat map of the attention. So if you see like a hypothesis like two kids are playing tag, and this is hard to read, and the premise is a young girl kisses a ring-bearing boy at a wedding, there should be no relation here, but it does see that there's a connection between girl. Is this supposed to be an entailment? Oh yeah, it does align pretty strictly here. So it tracks that there's some consistency that a girl and a boy and kids are aligned, and then uses that to inform its decision. Carl will have covered large-scale reading comprehension, but this is worth sort of thinking about from a memory standpoint. You have Did Carl cover? Okay, I should have checked what his slides were, but he didn't share them with me yet. So the task here, just to remind you, was that you had to read a long story of 1,000 or 2,000 words from a news article, and either before you started reading or after you were reading it, you would observe a question, which is a closed form query, so you need to fill in the gap, and you need to return the element that fills that gap. Obviously, if you try and do this as a sequence-to-sequence model, you need to capture a very, very long-range dependency, perhaps, and that's going to be difficult. Attention pushes the job of capturing that long-range dependency out of the state of the RNN, so you're no longer conflating controller and memory, and into just being able to find the most similar sort of element in the story given the embedding of your question. And you can, again, visualize what the model is doing by doing a heat map of attention and get really nice visualizations like this. So to summarize attention implements a form of read-only memory where you're not touching the memory once you've produced it initially, but it successfully mitigates sort of limitations of the original sequence-to-sequence model, in that it allows you to skip this transduction bottleneck, look back upon a large range of options when deciding what you're going to output next, and in turn that actually allows gradient to flow back. It's quite versatile and can be adaptable to many problems, and there are many forms of attention that I didn't cover here in detail, but early versions of memory networks by Facebook AI research can be seen as a form of attention as well. There are co-attention networks and a variety of fancy-sounding models that are also worth looking at. And it can be tailored to specific sorts of processes. So instead of just outputting, when you have this distribution over the attention matrix and outputting a vector, you can actually just directly use that as the softmax of your output, of the output of your controller. That's what's usually referred to as a pointer network. So you can point to words that you don't necessarily have representations for in the first place. Yeah, but so the limitations of attention are, first, it's read-only. So if you needed to if you needed to answer a question across a document that required looking at it several times and linking bits of information, so for example, in the story question answering task that Carl presented last week and I briefly talked about, you could imagine that there are some questions that require linking different bits of information. Attending several times means that you need to attend to one bit of information and also track the fact that you've attended to that bit of information and conditioned on that, attend to something else and put the information together. So this puts a strong onus on the controller for tracking what's been read. Instead, it might be more appealing to be able to update somehow the memory to indicate I've attended to this bit and I don't need to look at it again. The read-only aspect also means the encoder needs to do a lot of the legwork. You need to capture pretty good and you need to capture good representations on the encoder end in order for the controller during the attending phase to be able to differentiate different entities, for example, in question answering, or different sort of words in the textual entailment. So the encoder needs to do a lot of the legwork. So there's some limitations to it too. Maybe we'll take a 5-minute break here. Are there any questions briefly regarding attention before we take a break? No? Okay, great. Okay, let's take a 5-minute break and reconvene at 5:05 for the second half of this lecture, which should take no more than, I think, 30 minutes or 35 minutes. Okay. Do I need to do anything here?
Oh, I can stop that if you want, or you can just leave it there.
And
Okay.
I can play Snake that goes with you after.
Oh, thanks. I unfortunately have dinner plans already, but
I'm either going to the table.
okay. If no one else is taking a break,
Secondly, to say that languages are context free doesn't mean that they span context free. So you can take all the human languages and say to some rough approximation is a bit different than a context free class. But they'll only be a tiny slice of context free class. There's lots of context free rumors. There's never going to correspond to human languages, and you'd never be able to understand them. Well, people worry about this and they'll say, well, there's some things in there that you not agree with, that there's a class of chunks of problems free and so you can have all these. It doesn't matter if the whole class is programming, another sort of further argument is that do you believe humans are processing programmers or are they doing something more probabilistic? Of course, everything we do is typically probabilistic. So then more question of not learning and experiments that learning distributions. And that is different from what we get.
What's actually different probabilistic thing with experimental quantity is sort of got some flavor in there.
Yeah, so you can look at things like probabilistic quantity programming, but then the question is about discrete learning. More about something like how does one get to generating data. That in some sense seems much more natural because you can all be slightly off the right ground, but we in some way want to so it's okay here.
And as people hang out, they tend to get closer to people.
Yeah. But there's also a real place that doesn't really happen. So that the formal perspective happens to be.
Did anyone actually leave the room? Okay, if not, we'll just resume now, unless people want a longer break. So just to quickly summarize what we've sort of waddled through here. Someone did leave them. So the start of this lecture talked about limitations of RNN, induction bottleneck, and trying to argue that RNNs, as we know and love them in their basic form, are kind of at the bottom of this computational hierarchy. We talked about attention as a read-only mechanism, kind of to illustrate this process of stepping back from RNNs as a specific implementation of a model to this idea of having an API within which we could have this controller memory split, and to give an example about how the controller can interact with the memory. So in the last two parts of this lecture, I want to sort of return to this the computational hierarchy by talking about how this controller memory split has been used to produce kind of differentiable register-based machine or random access memory style controller memory interactions, and also push-down automata, which should explore the rest of the computational hierarchy we started with. So, yeah. So we'd like to let's jump across from finite state machines all the way to the top, or allegedly close to the top, which is Turing machines, where you can have a randomly addressable tape you can have a controller that moves over a tape and can make arbitrary, can read arbitrary locations, but also write to arbitrary locations. How would we do this in this kind of API? So we just saw attention as ROM, where based on either the previous controller state for late fusion, early fusion, or for the current controller state, there's an interaction between a read-only memory and the controller. What if the controller could also affect the memory state, which is now no longer immutable, but actually updated through time? That's the general idea behind neural RAM, neural random access memory, or neural register machines. And amongst this kind of class of algorithms, there are a large number of papers now. Initially, there was the neural Turing machine by Graves, Daniel Helke, and Greg Wayne. Then there were variants on memory networks where you could do multi-hop attention across the memory state and then re-embed it. There's neural GPUs, differentiable neural computers, neural programmers. There's a bunch of very general sounding names that fit that sound cool, but they all fit this general idea that we're going to have a controller that deals with input-output. It's also going to produce perhaps differently parameterized distributions over memory registers for the purpose of reading and writing. Reading will be the attention mechanism in most cases that we know and love. But writing uses that distribution now to decide, perhaps conditioned on some other part of the network, like what you're going to erase, where you're going to erase, what you're going to write, and where you're going to write it to. So contrary to the sort of RAM model we saw under attention, here both controller and memory state are updated at each time step. And the controller, the recurrent cell overall, produces the output in the next state. So this sketch of how this might work in a very simple context, obviously there's a bunch of variants, which I'll discuss briefly, but this kind of describes the first NTM paper, is that our previous state is going to unpack into the previous hidden layer of our controller, the previous state of our memory, and perhaps the last vector you read. The inputs to the controller are going to be the last read from the memory and the current input to the overall module. And by feeding those along with the previous controller state to the controller, so this would be a standard LSTM style update, you're going to produce the next state of the controller, but also not just one output, but several outputs. You're going to produce the overall output to the network, Y, which is going to be perhaps the next symbol you're going to generate. You're also going to produce a set of keys, so one or more keys for reading, one or more keys for writing, as well as one or more vectors that you're going to write, so you could have several read or write heads. You're going to use that read key to produce, by doing basically an attention style mechanism over the memory, produce a read vector which is going to be fed to the controller the next time step. So that's just like attention. But now we introduce this write stage, where instead of having an immutable memory, you're going to update the memory state based on the value of the vector output by the controller, the write, and the previous state of the memory. An example of how you might do this is you're going to use your write key very much like an attention query to produce a distribution A over the memory slots. And for each memory slot, you're going to multiply. Each memory slot, you're going to store the vector V weighted by how much you think it belongs there, and subtract the previous state of the memory based on how much you don't think the vector belongs there. So you're going to interpolate the previous state of the memory with the vector you want to write, where A is your attention weights. So this is kind of this very simple kind of RAM style mechanism implements a form of location-based addressing. So implements a form of content-based addressing. So based on your key value, which is a query, and the contents of the memory, you're going to produce a distribution over what you're going to read and where you're going to write. There are a bunch of extensions that have been explored in the literature, such as location-based addressing. So for example, instead of having an attention-style mechanism over the memory, or in addition to an attention-style mechanism over the memory, you could also have like a read position being contained in the memory state. And the controller's job now, instead of producing keys, is to produce a shift via convolutions, for example, over that, to update that read head. So it could say I want to shift it 0.1 down or 1 up, and actually move the read head over the memory very much like a tape. People have explored in, for example, the original NTM paper, the DNC paper, using a mix of this location and content-based addressing. Instead of trying soft addressing like attention, people have also explored hard addressing. So actually saying this is a random access memory, and I'm making discrete decisions about where to read and write, which means that you can't backpropagate through that decision, but you can use reinforcement learning-based methods like policy gradients, aka reinforce, to train it. So there's papers from Yasha Benja's lab that kind of talk about this. people have explored more esoteric or heuristic addressing mechanisms, such as using k-means to retrieve the top k matches and then have some form of sparsity in the addressing introduced through that mechanism. And then for both register machines and also attention, people have explored factorizing out the memory and the content. So instead of basically producing a distribution over positions based on the content, you have a separate set of keys or prefixes to the content, and you use that to decide the position, and then you retrieve based on the weights of the similarity between the key and that sort of addressable segment, the actual weighted mean of the contents. So this sort of general kind of idea of having the controller be able to not only read the sort of attention matrix, but also write to it, was initially sold as a neural Turing machine. I'd like to briefly talk about the relation between this kind of model and actual Turing machines. So contrary to RNNs, which couldn't sort of move over the tape, you could sort of see here that within the memory that's preserved through time and updated, you're internalizing part of the tape that you that formerly described as external in classical Turing machines. And the controller, through content-based addressing or location-based addressing or some sort of mixture of both, can control the tape motion. So there's some degree of decoupling between the input and output that the overall RNN is exposed to and how it's addressing its memory. And you could think of the RNN acting as a controller as possibly just actually being reduced to learning the state transitions in an actual Turing machine. So there's a nice sort of, this factorization actually yields a better correspondence to actual Turing machines in a sense. But ultimately, it doesn't really give you all the generality that you have in a Turing machine, because the number of operations you have in this paradigm is still operating in lockstep with an input and output. So if you're every time you read a symbol or output a symbol, you get to like touch your memory and read the memory, but you don't get to have an arbitrary number of operations on that memory at each time step. It's fixed by your architecture. So if you wanted to do something like implementing an n-log-ed algorithm like sorting, you'd have a bit of trouble, because you'd read in your unsorted sequence, and under this paradigm you'd have n steps to output the target sequence. You wouldn't get to have n log n steps in between to rearrange everything in your memory and do the pivots and the permutations if you're internalizing the quicksort algorithm. So because the number of computational steps is still tied to the data, you can't really learn anything beyond linear algorithms with this. If you read the NTM paper, they do show that it can sort. But there are there are linear time sorting algorithms like radix sort that are constrained by the range of data. You have to put bounds on the range of numbers that is being sorted, because you're bucketing things. And that's what I suspect it's doing. But you're not going to be able to learn with, even with this read-write kind of mechanism, you're not going to be able to learn quicksort from an NTM. So they're unlikely to learn on general algorithms, but the initial experiments with NTMs, DNCs, and a variety of these random access memory style neural networks do show better generalization on symbolic tasks. So I guess the take home here is it's a step towards Turing machines, but maybe don't go for it doesn't reach the top of that hierarchy like we wanted to. They've also seen, you've like NTMs and memory networks and a variety of these more sort of advanced memory mechanisms have also, as they've shown promising results on symbolic tasks, and in fact you may have heard of this baby data set, which is a set of language-like reasoning tasks. But they haven't been applied to actual natural language processing tasks, or fairly large scale or difficult ones, that much. And the reason for this is, while there's a nice intuition about what's happening, that you're doing random access memory, you're being able to store arbitrary bits of information in your registers. These architectures are quite complex. There's a lot of moving parts, a lot of hyperparameters, and they're therefore quite difficult to train, quite difficult to tune, and there's not a nice immediate mapping from like the purported capabilities of these architectures to the problems we want to solve. So the take home of this particular segment is if you should read these papers. They're important papers. They're interesting in that they take us far higher up in the computational hierarchy than RNNs on their own. But you shouldn't spend your summer research project trying to get a DNC or an NTM or memory network solving like all of natural language understanding, because you're going to spend a lot of time just trying to tune the model, and they're just difficult to understand. So perhaps in between, so we've started with finite state machines, and that's kind of where RNNs on their own are. We've looked at a kind of stab at adding attention, adding read and write mechanisms to attention to try and bring us up to the level of Turing machines, and that has difficulties because the models are complex and don't quite exactly reach the level of complexity that they advertise they do. But in between Turing machines and finite state machines, there's the class of slightly simpler computational models than Turing machine called pushdown automata, which are just adding a stack to a finite state machine. And those can model context-free languages. So what sort of work has been done in that space? So this kind of still fits the same sort of controller memory split that you see in a Turing machine, in a sort of in the RAM-based mechanism. So the controller is not only just passively reading stuff from the memory as an attention based on its internal state, but it's also being able to update the memory. But if the memory is something that looks like and acts like a stack, the update there is very constrained. There are a few works that have introduced such a kind of neural or differentiable stack. And I'll describe one of them here and then give you some pointers to the literature in the extra notes that we'll share after the lecture. But here the basic idea is you're going to have a controller that's going to deal with input and output and preserve its state. And it's going to have a differentiable sort of approximation of the stack to which it can write by either deciding to push a new vector, or it can update its memory by deciding to pop a vector off of it. And it also gets at each time step to read what's at the head of the stack. So crucially, it doesn't get to read the entire value here. It has a very constrained access, both in terms of reading and writing. A neural stack is a complex thing to model because typically we see stacks as very discrete sort of data structures. You're either pushing or popping. And the state is like either vectors at the head or it's below the head. If we're going to make things differentiable, we're going to have to introduce some sort of continuous relaxation of those operations, but also of the notion of a stack state. So one way of doing this is to think of a differentiable stack as being an RNN in its own right. It has inputs and outputs, and it tracks its own state. And we're going to I'll show you how to hook that up with a controller. The inputs are going to be a continuous push signal, a continuous pop signal, and a particular vector value, which you can interpret as the vector being pushed with this particular certainty. And if this is 0 and the pop is 1, for example, that's ignored. The state of the stack is going to be decomposed into two elements. One is going to be the values that have been pushed onto the stack historically, and we're also going to keep track of how much those values are still on the stack at a particular time step. Based on the push, pop, and value inputs, we're going to update the previous state to have new values and new strengths, and also output the read. If we want to hook that up with a controller, we can think that the controller's job is to read inputs from the environment, so read symbols that it might want to push to the stack, or it might want to like translate or output, or condition the output on, and it also needs to produce a particular output. It has its own previous state. The output of the controller is going to be several elements. It's going to produce the overall output of the RNN cell, which is the next symbol that it's going to predict. But it's also going to produce the signal for the neural stack, so the scalar push-pop signals and the value. And using that, we're going to update these things. I'll give you a little illustration of how this works. So this continuous relaxation of the stack, let's imagine that initially the stack is empty, and a controller at the first time step says, I want to push a value v1 with certainty 0.8. So up is the pop signal, which is going to be a value between 0 and 1. Down is going to be the push signal, a value between 0 and 1. We could imagine that they could compete with one another in a particular implementation. And I'm going to store in my value state, part of the state, that vector, and associate with it in the strength part of the state, the strength with which it was pushed. When I read the stack, I'm going to go down from the top. So here there's just one element, so we're only going to read this. And I'm going to weigh the values I see by their strength up until I've read a total strength of 1. So here there's just one element on the stack, and the read is going to be I'm just going to scale that particular value by its strength. So you can sort of imagine that the controller said, I'm 80% certain that I want to push this element onto the stack. So when I read the head of the stack, I'm going to see 80% of the strength of that vector. At the next time step, the controller says, I'm a little certain I want to pop, with certainty 10%, for example, I'm going to pop the head of the stack. And then after I've popped, I'm going to push another vector with certainty 0.5. So the semantics of popping is an update on the previous state of the stack. I'm going to go from the top of the stack down and remove strength from the previous state until I've either run out of values or I've run out of popping energy. So here, if I'm saying I want to pop with certainty 0.1, I'm simply going to look at the previous head of the stack and remove 0.1 from its strength. And then when I push, I'm going to add another vector, v2, from the controller with certainty 0.5. And I'm just going to associate that strength with that vector. So now when I have some sort of uncertainty over what's at the head of the stack, and that's going to be reflected in the read, I'm going to see my read vector, which is representing the head of the stack, is going to be 0.5 of the vector I've just pushed, and then 0.5 of what's left, which is going to be the vector below it. So there's an apparent discrepancy here in that there's 0.7 of this vector on the stack, but I'm always reading down to a unit of something belonging on the head. So in a sense, it doesn't matter if you had 1,000 vectors below it on the stack at this particular time step. I'm always going to stop reading once I've read a cumulative strength of 1. And then finally, and I'll show you how this relates to discrete stacks in a second. I just want to show how something is removed from the stack. So at my third time step, my controller, based on what it's reading, says, I want to pop with strength 0.9. I want to push with strength 0.9, a particular vector v3. So now it's very certain that it wants to pop a unit off the stack almost and push a unit on the stack, or nearly. So I'll start with the pop. The pop is going to be removing 0.9 units of energy from the previous head of the stack. So I'm going to remove 0.5 from the topmost vector of the previous state, and that will go to 0. And I'm going to remove a remaining 0.4, so 0.9 minus 0.5 of the next vector. So that will go to 0.3. And then finally, I will add a vector v3 on with certainty 0.9. So when I read when I read the head of the stack at this particular state, the read vector will be dominated by 0.9 of the third vector. So because I was very certain I wanted to push it, that vector is going to be like pretty certainly the head of the stack, and its value will dominate the read. V2, even though it's still within the sort of state, the value part of the state, has a strength of 0, so it's not going to contribute to the read. So logically speaking, it's removed from the stack. And then V1 is going to, regardless of how strongly it was on the stack, since there's only 0.1 of reading energy left after a read V3, is going to have a small contribution to the value of the stack. So it's important to see here that in the limit, if my pushes and my pop signals, which are here scalars, are always 0 or 1, so if the controller learns to, in the limit, emit things that are discrete like operations, then this will actually be exactly a classical stack. If this was 0.1 here, and if I pushed the v1 with strength 0.1, my read would be just the vector I've added to the stack, regardless of what lies below. Likewise, if here I had everything was units in the previous state, and I popped the strength at 0.1, I would remove exactly v2 from the stack and not touch anything below. So when the controller goes towards the ends of this scale between 0 and 1, we replicate the discrete operation of the classical stack. This sort, yes?
Is the length of the stack unbounded, or do you have to write?
Yeah, so in this case, I've illustrated this within bounded boxes, but mathematically there's no bound, right? In that it can continue to grow as I push v4, v5, v6. It can continue to grow upwards. And if we look back upon, I'm not going to go all the way back, but I talked about the RNN API, I talked about the previous state, and the next state is typically being tied. So maybe that's going to be the same domain. But here, if we want it to be unbounded, the previous state is going to be, for example, for the value segments, so stacking those vectors v1, v2, v3, that's going to be a matrix that's the size of your embedding times the number of time steps. And that's going to grow at each time step. So you're hidden, as you unroll the RNN forward, your state is actually growing. And you can, this is completely kosher from a mathematical perspective as well as from a computational perspective. You can implement it so that you're actually growing your matrix that's storing the values and strengths, and therefore you're actually modeling a stack of unbounded length. So if there are a few experiments you can do if you're now having a stack-enhanced RNN. I should add before I jump into those experiments, the mechanisms I described here for modeling a stack, if you instead of like pushing and popping from the same end, you appended vectors and then prepended them when you're removing them, and you remove them. So if you remove them from the top and append them to the bottom, you can also model other data structures like queues or double-ended queues. So you can evaluate these sort of stack and queue enhanced RNNs on a bunch of synthetic sort of transduction tasks like copying sequences. And we'll see some, or reversing sequences. So you can generate data that doesn't have any local sort of linguistic regularity by randomly sampling symbols and then deterministically reversing them. These tasks aren't that interesting from a sort of scientific standpoint because, a single line of Python will be able to, solve the problem for you. So it's not hard to find a solution. But I'll talk about why they're interesting for RNNs. Some more slightly linguistically motivated tasks might be transducing sort of subject-verb-object languages that might have sort of be generated by context-free grammars and reordering them into subject-object-verb languages while keeping the nesting. Or we could also try some sort of genderless to gendered grammar transduction, like if you were translating English into German, and you could use the stack or the queue to track what you've translated so far. So we implemented different forms of differentiable data structures like stacks and queues and double-ended queues where you can push and pop on both ends. When you're copying a sequence, an LSTM doesn't. When you're copying or reversing, LSTMs don't work. By that, we mean that when we train them, and then if we want to test them on longer sequences than they've seen during training, they fail to generalize. With enough training, they will start to be able to copy sequences within fixed bounds, but they won't generalize to general copying or reversing algorithm. A queue will solve the copying task, and that makes a lot of sense because all the controller needs to learn how to do is treat the differentiable queue like a real queue and start pushing all the information until it reads an end of sequence symbol and then start popping all the information off and outputting it. A stack, for obvious reasons, isn't good at copying because you push all the information in and then it comes off in the wrong order. Likewise, for reversing, a stack has the right inductive bias and a queue does not because it's going to come off in the wrong order. And since a double-ended queue can act as both a stack or a queue, it solves both problems. For the other problems, but these data structures typically work quite well. Although LSTM converges, we notice some interesting results in the learning curves. And we see this across experiments. Models, this is sort of, this is perplexity, this is accuracy over time. When we train deep LSTMs with 1, 2, 4, 8 layers on these tasks, we note that on the training data, they're going to take a long time to get to an accuracy of like 95 to 96%. So they're slowly going to start approximating the process of copying or reversing a string. And as soon as you try on longer sequences, they're going to catastrophically fail at the boundary. In contrast, if you enhance an RNN with a data structure that has the right inductive bias, so for example, a stack for reversing or a queue for copying or a double-ended queue in both cases, after very few training samples, it will just peak at an accuracy of 100. And obviously, it's like we knew for these problems that this data structure should be good. So that's not particularly impressive in its own right. But not only that, it will continue to generalize on longer sequences. And in a sense, this sort of shows that if we go back to my earlier example of internalizing roles by being more expressive, the stack-enhanced RNN, for example, can internalize the context-free grammar for well, this isn't the context-free grammar for reversing, but it can internalize a simple context-free grammar that allows it to reverse. Likewise, a Q-enhanced model can easily internalize the simple set of rules that would allow you to manipulate a discrete queue in order to copy effectively. In contrast, the RNNs are taking a very long time, and again, this is interpretation rather than proof, but this could be seen as them slowly but surely starting to internalize something that looks a lot like the regular version of that problem, so being able to read a bounded number of A's and then capture the dependencies to output the bounded number of B's, where A's are your source and B's are the copied sequence. So LSTMs are perhaps when you're looking at these learning curves, internalizing a very large number of roles because their computational complexity, their model complexity is significantly lower than what you can model when you have an RNN enhanced with a simple constrained memory. So there's a bunch of different architectures in the space. I wrote a paper at NIPS. There was a similar paper on a slightly different variant of continuous stacks by Julien Mikolov at the same conference, where they also modeled lists and linked lists. There are also stack LSTMs by Chris Dyer that have a slightly different sort of semantics, but are also quite interesting in this space. So to sort of wrap up on this notion of neural pushdown automaton, these initial experiments show that when you train these long enough, and you don't have to train them that long, these differentiable stacks allow you to have models that are decent approximations of classical pushdown automata, and that they can solve problems that pushdown automata should easily be able to solve. And they allow you to introduce this architectural bias towards recursive or nested dependencies by modeling those not through the activations of an RNN, but by exploiting the way in which the data structure allows you to order information. And you'd imagine that these sort of differentiable data structures should be useful for a syntactically rich natural language, where we're told that, okay, it's plausible that there's these kind of tree-structured or nested structures or arcing dependencies, and therefore that this should be applied to parsing and modeling compositionality. But there's been little work on actually applying these architectures because they're difficult to implement, slow to train, and ultimately they're still tied to the number of computational steps. We have the same problem that you saw with a Turing machine, with a neural Turing machine, in that you can't sort of take arbitrary sort of spans of computation before you start producing output. Otherwise, with two stacks, you should be able to reverse it. You should be able to copy a list. You just read all your inputs onto one stack, then spend n time steps flipping the stack onto the other stack, and then you'd output the things in the right order. But because the model has no way of sort of, when you're doing supervised training, of learning to decide whether or not it's an output mode or if you're doing this contextually dependent number of computation steps, you can't learn these sort of algorithms. So again, like the neural Turing machines seeming to say, okay, it's a nice step in the direction of going that far, as far up in the computational hierarchy as Turing machines do, but not quite getting there. This is a nice step toward taking us from finite state machine approximators to push-down automata approximators, but perhaps not the complete step. Anyway, to quickly wrap up some of the take-home messages from this lecture, looking at these stacks and neural Turing machines and queue-based models and attention mechanisms show that it's fairly easy to design a very complex model that has some strong intuitions behind what form of computation it's doing. And while people will sell these models to you with carefully selected experiments, and I'm probably equally guilty of that, it's not always worth it in that those experiments don't necessarily tell you much about how well these models will operate on real complex problems like natural language understanding, where there's ambiguous data, and on top of it there's a lot of data. Perhaps from the perspective of understanding the literature and devising your own kind of models as part of perhaps your research projects during the summer, it's much better to understand the limits of current architectures, as we started by doing with LSTMs and RNNs, and trying to see how you can extend those very simple architectures to overcome those limitations. So one might say that attention sort of like fell out of this analysis. A nice example of this sort of scientific process of understanding the limitations of a particular architecture and trying to come up with a solution is illustrated in chapters 1 through 3 of Felix Gur's thesis, where he is one of Jürgen Huber's students who introduced the forget gate to LSTMs. It's really good chapters I recommend reading, because there's an analysis of the vanishing gradient problem for sort of traditional RNNs. And it's presented in such a clear way that the solution is like, when you're reading it, is just obvious. It's like, let's add some input and output gates and some forget gates. And guess what? That works pretty well. So you should not be just thinking about like what you're trying to model from a computational perspective, although that should be at the back of your mind, but also think about sort of the complexity of the problem you're trying to solve, and does the level of expressivity or computational ability of your model match that problem. But feel free to be creative, because otherwise it'd be really boring. Anyway, that's all I had to talk about today. But if you have any questions, we can take them now, and if not, some people are going to go play pool. Thanks. Are there any questions? Oh, thanks. No, great. Okay. Oh, yes.
Where would you, if you were to apply this to natural language, what architecture do you think is still simple but slightly more advanced than just using LSTM as far as the first jumping off point for language modeling or something like that?
Sorry, can you repeat? What was the?
What memory architecture would you use first? I mean, so no-turing machines, like you said, are really complex and hard to train and all that stuff.
I mean, where would I start? I mean, I'd start with the simplest thing possible first. So if you have a new problem and you want to start to try solving it, the right procedure is usually take the simplest kind of architecture you have readily implemented or can easily implement, and see how far that gets you. A common sort of crime that both PhD students and then more senior researchers will do is get very creative and start coming up with something that's very plausible when they describe it, but then and that might actually help, but then reach a point where they're not clear on which part of the monster they created actually does the legwork in producing better results, and then you get lost in larger ablation studies. Whereas if you start from a simple model, say, okay, these are the kind of mistakes it's making, these are the cases where it fails, let's think about how I can extend it so that it's easier to train and it iterates faster, or it's able to express the kind of dependency that it's not currently capturing and actually making fewer mistakes. That iterative process is much richer, because as part of how you're increasing the complexity of your architecture, you're also doing the ablation study in real time, in a sense. So that's the general methodology I'd recommend. In terms of what problems to tackle, which I think was the other aspect, I don't know, that's really like dependent on what you're getting for the exam or the practical, or what you want to spend your research project on. It's difficult to give a recommendation there. But yeah, I mean, like this thinking in terms of the model hierarchy is a nice starting point. To see if you're fine with an LSTM, in which case it's overkill to give attention or stacks or Turing style RAM. And if that doesn't work, then try adding something that, if not explicitly modeling a discrete stack, is capable of capturing dependencies without having to go through the activations, and then start stepping your way up. Yeah. Yes?
Is there any work on filtering or masking the updates to the memory? And the reason for that is if you have some data where you know there's a strong correlation, but you actively don't want your predictions to include that information.
If you have some data where there's some information and you want to ignore it,
yeah.
Well, you
So you know that although it seems that it's very strong, it will affect generalization later. So you don't want to include that information.
I mean, just for like the models we looked at today, you can assume that if part of your network is tasked with making that decision as to whether or not some information is salient or not, which you hope your controller would do in the examples we saw today, it can choose to like not push to a stack, or it can choose to, in the NTM, you could imagine that you could have a write strength prediction. And if that's 1, then you're writing the vector to the position that you've got from your write key, and if that's 0, you're not doing a writing op at that time step. And that would be one way of modeling this sort of like salient information selection. Now, whether or not the model would learn to do that is another problem. But you can always express these sort of things in the architecture.
You could pre-train the operation.
Yeah, maybe that's the right way to do it.
People use normal regularization for these kind of memories. Like, can you just like drop out memory or something like that?
Yeah, I mean, so generally speaking, with any recurrent networks, you need to, I mean, they're very good models of the joint probability of a sequence conditioned on the source, or in the language model, the joint probability of the sequence. And so people experiment, like to not overfit the training data, people play with a variety of dropout mechanisms. Now, whether or not this interplays with the memory, well, I don't think has been explored in a large amount of detail. So I didn't, for example, do dropout when I did the stack-based experiments, but it's plausible that it would help, because if it doesn't see a bit of information, but it could piece it together from what's in the memory, in the case of an attention-based memory or a RAM-based memory, then it would perhaps benefit from using the memory more explicitly to compensate for occasional lapses in observation during training. That's good. That's not a bad idea. With regard to regularizing weights, it seems less fashionable for some reason to do things like L1 and L2 regularization in RNNs, but there's no reason that shouldn't be a good idea, both in just normal RNNs and in memory-enhanced RNNs. You would be careful not to like do things like regularize, or maybe you'd want to regularize the contents of your memory not to be very peaky. I don't know. I mean, you could put sparsity priors also on the contents of your memory, but with L1 regularization on the activations, perhaps. I don't know. I don't think people have explored that much, but it's perhaps a nice thing to look at.